Hi everyone, in this video I'm going over the practice exam for exam 1, which is coming up soon. I'm going to start on number 16 because 1 through 15 are really more like pre-calculus type problems. Feel free to try those problems if you want to brush up on your algebra, but 1 through 15 won't appear explicitly on the exam. Exam material really starts at number 16. So I'll pick it up there. It says, on Earth, a ball is thrown into the air with an initial velocity of 30 feet per second. Its height in feet t seconds after being released is given by this equation here. Find the average velocity for the following intervals. So we're going to start at 2 seconds, and then we're going to let a little bit of time run. And that'll be a tiny interval. And because that interval is so small, we'll really be approximating the velocity right at 2 seconds. But let's just perform the problem. So for part 1, to find the average velocity, we would want to plug in, basically I'm going to use this piece as T2 and this piece as T1. And I'm plugging those times into this function. So I'll have that the average velocity is h of T2 minus h of T1 over T2 minus T1. So to actually carry that out, we would have, so now I'm plugging 2.01 into h. And then I have to subtract, plugging in T1, which is 2 into h. And then T2 minus T1, so 2.01 minus 2. Some quick arithmetic. So you can plug all this into your calculator. I believe you're going to get negative 34.16, and that would be feet per second. For part 2, it's very similar. Maybe I'll use a different color for part 2. We're plugging in now 2.001 for T2, so we're even closer to 2 now. And still using this thing here. So 30 times 2.001 minus 16, 2.001 squared minus, and then we have the same thing here actually. And then over 2.001 minus 2 this time. And just doing that quickly, 34.016, and that would be feet per second, the units on that. Okay, so yeah, perhaps on your exam there was like a 1, 2, 3, and 4. So 1 and 2 here are 3 and 4. So I just did 3 and 4 essentially. But okay. And as far as what would be the instantaneous velocity exactly at 2, I'm guessing the closer and closer we're getting to 2, the closer and closer we're going to get to negative 34. So I'll just make that my guess. All right. That's number 16. I'm moving on to number 18. So this one says, guess the value of the limit of this expression as x approaches 3, we have x minus 3 over x squared minus 9. It says by taking values very near, above and below, x equals 3. So I'll let this side be my less than 3. I'll let this side be my greater than 3. I don't know why I wrote 0. So greater than 3, less than 3. So just to pick some values, and by the way, we need to guess the limit here because plugging in 3 doesn't work, right? 9 minus 9 in bottom. So we're almost stuck with this numerical approach, right? So this is what I've been calling the numerical approach. Sorry about that. So maybe 2.9, 2.99, 2.999, 2.9999, right, you're getting the point there. And then maybe on this side, I'll go 3.1, 3.01, 3.001, so on. Okay, so what I would then be doing, and I'll show you maybe just one occurrence of this. So I would now be taking 2.9 and plugging it into here. So 2.9 minus 3 on top, and then 2.9 squared minus 9 on bottom, hit equals, and then I can press this S to D button to transfer that into a decimal. So it's this strange decimal. I'll just approximate it, okay? Maybe I'll write it in blue. So 0.16949, and I'll just say 153. Okay, so what I would then do is what you can do on this calculator is press left, I guess up, and then left. And then you can just edit, place another 9 there, so you don't have to type everything else again. And here's this next number, and I'll just write down some of those digits. Okay, so I'm just going to continue. So if you were to evaluate these other ones, you would get numbers like this. Please check your work and check my work. And then finally, okay, and then we'll get numbers over here. And I'll just write the last couple down to save a little time. So we'd have 166. And then this final one would be so as these numbers are getting closer and closer to 3, which is what we're supposed to do because the limit we have x approaching 3. It looks like we're getting more and more close to a number like 0.166666, and then it appears this 6 continues forever, right? So that would be my guess. So I'd say my guess is 0.16, and then I'll put a bar over the 6. So that bar means that that 6 will continue forever. So if I type that into my calculator, it's kind of hard to. I would just need to go 0.1 and then just type as many 6s as the calculator might allow. And it actually approximates that. perfectly. So it says, okay, that's essentially going to be 1/6. All right. Moving on to number 20. So it says, guess the value of this limit. And I kind of provided a graph here, so apparently you can graph this and get a better sense for the limit. Keep in mind, whenever you're finding a limit, you can always plug in. That's like step one, is plug in. If you can plug in and you get a number out, you're done. So if I plug in, so I'm supposed to be looking at the limit as x approaches 0 of f of x. So what if I just plug in and see what f of 0 is? That direct substitution property. So for inputs like 0, we're looking at x is less than or equal to 1, right? That would fall into this category, right? Since x equals 0 is less than or equal to 1, that means I'm looking at this quadratic piece and not this linear piece. So I would have f of 0 equal to negative 0 squared minus 4. So in other words, that would be negative 4. So that's not a guess. Okay, so that's actually the limit. Let's graph this thing. So it looks like we would have this quadratic opening down, kind of like this, but then it would just hit right here with this open dot. Right there, I guess it would be closed, technically, yeah, because of this inclusive. And then up here, we'd have this linear piece. So we'd have an intercept of 2, but it's not inclusive there because we're just starting from greater than or equal to 1. So at 1, we'd have positive 1. So I'd have this open hole, which is not really a hole, but it's just an open point there. And then we would have this negative 1 slope thereafter. So from this graph, you can see what the limit is also, right? If you approach 0, then you're traveling along this piece of the function here on the left. If you approach 0 from the right, you're still on this function. So those are those values. You're approaching that value of negative 4. Let's go down to number 22, and as a reminder, I will be posting a key to all the problems, but I'm just doing a subset on the video. So evaluate each limit. Remember, first step with these limits is plug in. If you get a number out, you're done. Okay. If you don't get a number out, like if you have some mathematical error, then you may need to do some algebraic manipulation, and then you plug in again. And if you get a number, you're done. If you don't, maybe some more algebraic manipulation. Okay, so I'm going to plug in just to see what happens. So we get 3 plus 1 plus 1. Looks like we get a 5. So plug in, we got a number out. So I'd be done there. Let's look at number 23. So yeah, let's plug in. So plugging in, we would have 4 squared minus 4 times 4 over 4 squared minus 4 minus 12. And that would be equivalent to 16 minus 16 over, so this would be 12 minus 12. So this is like a 0 over 0, and it's really this 0 in bottom that's the issue. The 0 in top is not a problem. So this means do some algebra. So it looks like we can factor. So I'll rewrite it as x minus 4 over x minus 4, x plus 3. So this can be canceled away. So in other words, this limit is the same as this limit. And after you do that bit of algebra, then plug in again, right? So that's like number 3. After you do this, you go to number 3, which is plug in again. So if I plug in, I would get 4 over 4 plus 3. In other words, 4/7. Down here, number 24, the squeeze theorem. All right, so with these, we need to kind of build on a safe fact. So from trigonometry, and again, we're not trying to kind of find the value of the limit, right? We know it to be 0, we're just trying to show it. So we're trying to show the logical steps that lead to this fact being true. So from trigonometry, we have that the sine function is bounded above by +1 and below by -1. Okay? If I multiply through by what we're missing, meaning this piece, x squared, then we would have this. Okay, since x squared is never negative, we do not have to flip, quote unquote, the inequality symbols. Remember, whenever you're working on an inequality, and you multiply or divide by a negative entity, you have to flip each symbol, right? And since we multiplied through by x squared, that is never negative. So we do not have to worry about that flipping of the inequality symbols. So the only thing I'm missing is the limit, so I'm going to attach the limit now to everything. So limit as x approaches 0 of -x squared less than or equal to the limit as x approaches 0. All right. The thing about this is we can find the limits of the outer piece of this compound inequality. The whole problem is we can't plug in 0, right? And we're not really doing a numerical thing because we want a more formal justification. The numerical approach gives you a sense, but it actually doesn't show it. So here, to evaluate this limit, we can just plug in. So plug in 0, square 0, we get 0, multiply by -1, we still have 0. So we would have 0 is less than or equal to the limit. So x approaches 0. X squared sine of 1 over x. Less than or equal to, again, plug in 0. we get 0. So hence, the limit as x approaches 0, x squared sine 1 over x equals 0. And I'll just say by the squeeze theorem. All right. There won't be any like 25. Okay, so I'm going to move on to 26. So this says basically, where is this function discontinuous? So I'll go ahead and graph it just to help out. It's not totally necessary, but I'll go ahead and do that. So less than or equal to -1, we have this linear function. So if I plug in -1, I'd have 2. And then we would have this positive slope thing happening. So less than or equal to, so it's a solid dot there. And then we have this exponential piece for x is strictly greater than -1. So if I look specifically at -1, we would have 1/2. So I'll have an open dot at 1/2. And this exponential behavior after that. So we have a discontinuity at x equals -1 because the limit does not exist. Remember, we had those 3 criteria for continuity. So if you look at the left-handed limit, the values are going up here to 2. If you look at the right-handed limit, the values are going down here to positive 1/2. So that left-handed limit does not match up with the right-handed limit. Therefore, the double-sided limit as you approach -1 does not exist. So the limit as you approach -1 of f of x does not exist. So that means there is a discontinuity at -1. So I'll just say it that way. Okay, moving on to number 27. This one says find the interval over which each function is continuous. All right. So we had in the book, I'll reach for it and see if I can find it, but it said somewhere in here, right here, this is on page 25. So it said the following types of functions are continuous at every number in their domains. So root functions. So if I find the domain of this function, then that'll tell me a lot about the interval of continuity of this function. Okay, so since h is the square root function, I need that 1 plus x is strictly greater than or equal to 0 for the domain, if I think of domain. So subtracting over this value, we would have x needs to be greater than or equal to -1, right? For domain, we would have this, right, in interval notation. For continuity, we never include. So for the interval where this function is continuous, I'm going to say continuous at parentheses, -1 to infinity, parentheses. Okay. Yeah, let's go on. All right, this will be the last one, number 28. It says, use the intermediate value theorem to show that there is a root of the given equation in the specified interval. So I'll do part 2, actually. So what I'll choose to do is actually bring everything to the left. So I'll subtract 3, I'll add 2x. So I'll subtract 3, add 2x to the left. So e to the x plus 2x minus 3 would equal 0 in that case. And we still have this interval that we care about. So I'm going to let this piece be f. So f of 0 would be e to the 0 plus 2 times 0 minus 3. This would be 1 minus 3. This would be negative 2. F of 1 would be e to the first plus 2 times 1 minus 3. This would be e minus 1, which is positive. So this is negative, this is positive. So in other words, the function goes, and if we're looking just from 0 to 1, it goes from negative over here, and then at 1, it's somewhere over here. And it's continuous, okay, that's an assumption. So I'll say, with all that, so since we got negative 2 and e minus 1, which is greater than 0, which is a positive number, we know by the IVT, the intermediate value theorem, that there exists a root of f in 0 to 1. So that's kind of the final answer, but this is the support. All right, good luck on your exams, you guys. Talk to you next time. Bye-bye.